In this video, we are going to talk about charges and its properties. Now, what is a charge? In simple words, charge is just a property of matter. Now, just like mass, matter can have charge. If you go by the basic atomic model, then there is a nucleus which contains nucleons, and then revolving around this nucleus are electrons. So the most elementary unit which matter is made up of are atoms. Now you can go beyond the atoms and then you can say the new discoveries have led to mesons and quarks and whatnot. But at this level, we are going to assume that atoms are the basic units which matter is made up of. So if you have a lot of atoms, it will give you a bulk of anything. Now the nucleus contains nucleons, which are protons and neutrons. So the three elementary particles which everything is made up of are electrons, protons and neutrons. Now it has been found out from experiments that out of these three, two are electrically active. So electrons and protons have charge, whereas neutron doesn't participate in this electrical activity, and you can say that it is chargeless. Now take a simple observation. It has been found out that if you take two protons and keep them near to each other and release, then they're going to run away from each other. The similar thing happens with electrons as well. If you keep two electrons, they're going to run away from each other. But if you keep a proton and an electron near to each other, then they attract and run towards each other. Now, what conclusions can you draw by this simple observation? The first conclusion that is very prominent is the charges are not the same, but they are of two types. The type of charge that electron has, proton has exactly opposite type of it. Now, because there are only two possibilities, therefore we call one as positive and the other one as negative. Now this is done to make the study easier. So conventionally we call the type of charge on protons as positive and type of charge on electrons as negative. And neutrons are neutral, so if you keep neutrons near to any of these particles, no electrical activity is going to happen. Obviously, neutron still has mass and you'll see a slight attraction between the particles if you observe very keenly. Now let's come to the unit of a charge. In metric system, charge is not a fundamental quantity but a derived quantity. So in metric system, current is a fundamental quantity. And you know that current is defined as charge flowing per unit time. From here I can write charge as current into time. The SI unit of current is ampere and time is seconds. So the SI unit of charge is ampere seconds. If I talk about the dimensions of it, then this will be ampere time. Now this ampere second has a special name because this quantity charge is really very important. It is called coulomb. So 1 ampere second is equal to 1 coulomb. Now this coulomb comes from the name of French scientist Augustin de Coulomb. Now let's talk about the magnitude of the fundamental charges. It has been found out experimentally, and all of this is based upon concrete evidence by observations, that the magnitude of charge on one electron as well as one proton is 1.6 into 10 raised to the power minus 19 coulomb. So that's how small the charge each electron or each proton carries. But now the types are different, so the charge on electron is called minus 1.6 into 10 raised to the power minus 19, whereas charge on proton is plus 1.6 into 10 raised to the power minus 19 coulomb. Now don't make a mistake of thinking that the charge on electron is lesser than the charge on proton. As I told you, the magnitude is the same, but to differentiate between their types, we put the signs. So this doesn't mean that the charge on proton is 3.2 into 10 to the power minus 19 coulomb more than the charge on electron. So don't be confused, let it be clear. I'm sure you would have heard about conservation of mass. It's such an important law that everybody knows it. But there is a similar law in electrostatics as well. That's called conservation of charge. To explain it very simply, assume that there is an isolated box, and inside this box there is a charge of x coulomb. Now if you don't allow any charge to come inside this box or any charge to leave, then with time this charge is going to remain constant, or we can say that in an isolated system charge is conserved. One caveat here is I'm not saying that charged particles are conserved. So if there were, let's say, 5 particles at the time when you saw the charge to be x coulomb, and suppose that you come some time later, then it might happen that the number of particles can change. But if you measure the summation of all the charges each particle carry, then you're going to get the same amount x. So don't misinterpret this statement as law of conservation of charged particles, but this is law of conservation of charge. So it means that if there is any body in which there are more protons than electrons, then it will have a net positive charge. Whereas in a body where the number of electrons are more than the number of protons, the body will be negatively charged. But if a body is neutral, it doesn't imply that there are no fundamental particles inside the body. If it has mass, then it has to have charge. But if the body is neutral, it implies that the number of electrons and number of protons are equal. Now let's talk about quantization of charge. Assume that there are only 1 rupee coins available in the market. So there are no other currency that is available, and any amount that you have to make, you have to accumulate 1 rupee coins. In that case, suppose if I want you to get me 100 rupees, how many coins would you need? 100. Because each coin corresponds to 1 rupee and there is no other currency. So in this case, I can refer to this as quantization of currency. Similarly, there is quantization of charge. It means that if any negative charge is made up of electrons or any positive charge is made up of protons, this implies that any charge will be a multiple of this basic charge. Suppose a body has y coulomb, I can say that this y coulomb is made up of integral multiple of fundamental charge. This will be equal to integral multiple of the magnitude of least charge that is available. So I can say that if this is so, then y coulomb must be equal to n times, where n is some integer, into E. But wait, I have a question for you. If everything is made up of fundamental particles, then why only charge is quantized? Why not mass? Can I say mass is also quantized? Think about it. Well, to give you an answer, masses of electrons, protons and neutrons are different. So suppose the mass of an electron is me, mass of proton is mp and mass of neutron is mn, then I cannot say that any mass m, capital M, which is the mass of any matter, will be equal to some integral multiple of me, because there can be protons or neutrons. To make this more clear, let's find out how many protons would be required to make 1 coulomb of charge. So I can say 1 coulomb of charge will be equal to number of protons into magnitude of charge on each proton, which is 1.6 into 10 raised to the power minus 19. This gives me the number of protons required to make up this 1 coulomb as 1 divided by 1.6 into 10 raised to the power 19. So you can figure out this number, but I can see that this number is really huge. Similarly, if I want to make a charge of minus 1 coulomb, I would need these many electrons.